Hello, this time I'm going to give some background on one of the greatest of the greats in physics, James Clerk Maxwell, who of course is most famous for formulating Maxwell's equations. This is the first time that electricity, magnetism and light were described as being a single phenomenon that were manifesting in different ways. So he was unifying those different, which at the time were seen as separate entities. He was unifying those together, and this is why this is called, the second great unification of physics, after the first great unification, by Isaac Newton in the 17th century when he was unifying gravity. So this is real paradigm shifting stuff, completely revolutionary in physics, science, just in the world, really, everything that's come off of the back of it. So yeah, groundbreaking stuff. So Maxwell was a Scottish physicist and mathematician. He was born in Edinburgh to a sort of comfortably off family. They moved to southwest Scotland when he was a child. He was initially educated by his mother, but she died when Maxwell was only young. He was about 8 at the time that his mother died. And then his father and his aunt then continued his education. At the age of 12, he went to a demo of electric propulsion and magnetic force. This was by Robert Davidson. This is the guy who built the first electric locomotive. So the first electric locomotive was built in 1837. So not long after that, Maxwell went to see a demonstration by this guy, and it had quite an impact on him and his interest, seeing this new science and engineering at the time. He then continued in his teen years. He got educated at Edinburgh Academy, one of the main prestigious schools in Edinburgh, and he won prizes in a range of subjects. I mean, not surprisingly, maths, but also English and poetry and such like. He then moved from Edinburgh Academy to Edinburgh University, where he also he continued private study alongside his lectures, because a lot of it he was apparently finding quite easy at the time. So it gave him opportunity to pursue his own interests. And he constructed his own equipment, chemical equipment, electric, magnetic. So all this apparatus he was putting together, and he could then pursue his own scientific investigations. He started initially by looking at polarized light. He was getting blocks of gelatin and then stressing them and passing light through them, and then seeing what the results would be and how the different stresses on the materials would polarize the light in different ways. Age 19, he then moved from Edinburgh University down to University of Cambridge, and here he developed not only his science, which kept on going as it did throughout his what was sadly quite a short life, but also his strong Christian faith as well. So yeah, he had both aspects there to his life, and it was during his time at University of Cambridge that he then demonstrated that trichromatic theory, as in having three colours, your red, blue, green, that if you mixed red, blue, and green light together, you'd get white light. The idea of mixing different coloured lights together to get white light wasn't new. This is, people like Newton had done this, 150 or more years beforehand. But in terms of having those three primary colours, this was relatively new. And Maxwell was using coloured spinning tops, with the three colours on, and then spinning those, and then demonstrating that could produce the effect of white light. Age 25, he then went to a college in Aberdeen. This is one of the precursors of Aberdeen University. So he moved back to Scotland, and he was a professor at age 25. I mean, the other professors there were pretty much all age 40 or more. So he was, he was quite ahead in terms of his years, and he was lecturing there. He was setting the syllabus and such like. He began new studies, so he started looking at the rings of Saturn, and these have confused scientists for a couple of hundred years since they were first observed. And Maxwell used his skills as a mathematician to show that if the rings were solid or they were fluid, then they would be unstable. So he concluded that they must be rings made up of lots of little bits, each of which is orbiting, largely independently around Saturn. And of course, this is how we view the rings nowadays. But this wasn't really confirmed observationally until, I suppose, the early 80s, when the Voyager satellites went past. So, yeah, again, groundbreaking stuff. The college that he was at in Aberdeen then merged with another college to form the University of Aberdeen, and he became unemployed. They then had to jettison some of the lecturers and professors that they had, and despite his achievements, he was one of the ones who was then seen as being surplus to requirements. So as a consequence, he then moved down to London, to King's College, London, in 1860. And this is where he first met Michael Faraday. So, really starting to get back into electricity and magnetism again. I mean, Faraday was about 40 years older than Maxwell, but he made a lot of public demonstrations and such like. He was a very public scientist, and it was during his time at King's College that Maxwell made all of his great discoveries in electromagnetism, which I'll get onto in a bit. After about 5 years at King's, he then resigned. He went back to Scotland, and he stayed there until about 1871, thereabouts, and then he became the first Cavendish Professor of Physics at Cambridge University. And as I say, he didn't live for very long. He was only 48 when he died. He died of abdominal cancer, which is what his mother died of, and at the same age as well. They were both 48 when they died. So, yeah, doubly tragic. Getting on to his discoveries, I mean, his path to Maxwell's equations, it was a long one. I mean, he started work on electricity and magnetism in his early 20s, so we're still in the 1850s there. He was commenting on Faraday's work, the relationship between electricity and magnetism, and Faraday's experimental findings. And he took the knowledge of the time and he reduced this down to 20 differential equations. They were all interlinked in some way, but he had these 20 variables in 20 equations, and he published this in the 1860s. Then, when he was at King's in the 1860s, he also calculated that the propagation of electromagnetism, if you've got an electromagnetic disturbance, he calculated that propagates at the speed of light, a discovery that he considered to be more than just a coincidence. This was then him making this connection between electricity, magnetism, and then light. And he then, in 1865, he published a paper describing light as an electromagnetic disturbance. And he then went on from that. He did a new, sort of more developed form of his 20 equations that he then published. That was in 1875. And with the help of Oliver Heaviside, who reduced these equations down, he was condensing them down to the 4 equations that we now know as the Maxwell's equations nowadays. So it was reduced down to these 4 partial differential equations. So this both described electricity and magnetism mathematically, and it introduced the idea of electromagnetism as a field. It introduced that idea, the electromagnetic field, rather than just talking about the effects of electricity and magnetism as lines of force in the way that Faraday was describing them. So it was moved from this idea purely of force to fields propagating through space at the speed of light. Of course, this still left problems, as we know from what then subsequently happened in the early part of the 20th century. You had difficulties around, well, what is the medium of propagation? If you've got this field which is propagating, and you've got light which is propagating, and they're moving as waves, well, what is the medium that they're propagating through? And of course, we looked at this in the wave section, Michelson, Morley, and such like, and the experiments there. And you've also got the apparent problem of needing an absolute frame of reference. Um, you know, we're talking about various relative motions and how things are moving around, and they still had that difficulty surrounding the speed of light and what frame of reference are you measuring it in order to have this speed of light, which of course turned out to be independent of frame of reference, that it's got this fixed value throughout the universe. But of course they didn't know this at the time. This was something that was only figured out later on in the 20th century, work by Einstein and others. Aside from setting up Maxwell's equations, which of course was enough to make anyone an absolute titan of physics, his work on colour also extended to looking at colour vision, colour photography. He was moving on with this trichromatic colour theory that I mentioned earlier, and following on from the work of Thomas Young, and he created the first colour photograph. He combined three photos. He was saying, well, if you take three photos of the same thing through a red filter, a green filter, and a blue filter, then combine those, well, you'll have yourself a colour photo. This is just the same trichromatic theory put into practice. Okay, the first result wasn't that great because the photographic plates weren't that sensitive, particularly to red light. But the principle stood, and it was enough to at least show that it was a possibility. Of course, we've also encountered Maxwell in thermodynamics in earlier videos, where he was developing a theory of the velocity distribution of particles in a gas. We've spoken about the Maxwell-Boltzmann distribution. It was Ludwig Boltzmann who then generalized Maxwell's findings, and then that's where the Maxwell-Boltzmann distribution came from. So they weren't working together, they were working on the same problem, and Boltzmann just came that a little bit later. In his work on thermodynamics, he also came up with a very famous thought experiment, often referred to nowadays as Maxwell's demon. It was a thought experiment about the second law of thermodynamics. Now, the idea is that you've got this box of gas. So imagine you've got this big container full of gas, and it's got this divider in the middle with a door on it. And there's a demon in inverted commas. This is what Lord Kelvin described it as. So you've got something, some kind of agent, which is opening and closing this door. So it lets fast molecules move to the right. So if they're coming towards the gap and they're fast, it will open the door and let them go through to the right-hand side. And similarly, going the other way, if you've got a slow molecule going to the left, it will let a slow molecule go through to the left-hand side. So you end up getting this accumulation of the high energy particles on the right-hand side for high temperature, and the low energy particles on the left-hand side for low temperature. So you're actually sorting things out here. You're creating some kind of order. You're decreasing the entropy of the system, if you think back to our thermodynamics, apparently without performing work. So there seems to be some kind of process that's going on here which doesn't require an input of energy if the door is frictionless, or whatever is required. If you're not having to put energy in, and yet you're still managing to sort these particles, then aren't we violating the second law of thermodynamics here by reducing the entropy of a system? Now, there's been a lot of discussion over the last 150 years or whatever over the solution to this problem. I mean, not surprisingly, most attempts are centering around the entropy of the demon. This demon is involved in the system in some way, but it's trying to pin down exactly, really, in what way the demon and the system of gas and particles interacting. The demon needs to have some way of measuring what the molecular speed is in order to make the decision as to whether to open the door or not. So there's certainly an interaction there. There's some kind of build up of information about the behavior of the particles in the gas. So what is actually happening in terms of that interaction between daemon and system. So if you're going to preserve the second law of thermodynamics, then you need the entropy of the daemon, or the information of the system, what we know about the system, to be increasing faster than the decrease in the entropy of the actual gas particles themselves. But yeah, Maxwell's daemon, it's something which has been fruitful for philosophers of science over best part of 150 years. So yeah, I mean that's Maxwell. I mean, you could talk about this guy for days, the amount that he's covered. Maxwell's equations in themselves, as I say, are completely paradigm shifting, revolutionary. This is why this guy is often put in the top 3 of physicists of all time, along with Newton and Einstein, because it's just one of those, every few centuries breakthrough that you get in science. In the way that Newton did with gravity, Maxwell's done with electricity and magnetism, and then Einstein did with relativity. So you can see why he's right up there with the biggest names, even though he isn't generally as well known, amongst the public when it comes to the names of their scientists. Probably because it's more mathematical. It's harder to get a grip on what was going on with Maxwell's equations as it is compared to, say, people understand gravity a bit better. Einstein was quite the celebrity physicist with the way that media and culture was going in the early 20th century. So Maxwell didn't have quite the same sort of social impact that Newton and Einstein did. But yeah, an amazing guy and a tragically short life, but well, the amount that he achieved, astonishing.